All right, for now this chapter, we start something completely different. We've just finished inorganic chemistry. Now we're going to be looking at organic chemistry. And organic chemistry is primarily going to be carbon-based. That's the definition of organic chemistry, is that it's going to be carbon-based. So we're going to be looking at lots of chemicals that have carbons, hydrogens, oxygens. Some will have sulfur, some will have nitrogen. But this is going to be organic chemistry. And the interesting thing about organic chemistry is you look at just carbon-based compounds, so you're looking at just basically carbon, hydrogen, primarily a little bit of nitrogen, a little bit of oxygen. There can be almost in excess of 10 million compounds based off of organic chemistry. So it's a very immense science, very somewhat difficult. There isn't any math going to be in this portion. Primarily it's just going to be the chemistry, which should be a little bit difficult. So for the very first problem we're going to do, it asks us, draw the condensed structural formula for alkanes or the skeletal formula for cycloalkanes for each of the following. All right. So what we're going to do is we're going to do both. We're going to look at the condensed structural formula for all of them, and then we're going to look at the skeletal one. All right. So for the very first one, we're going to have propane. Now propane, prop means there's 3 carbons. So that's going to be 1 carbon, 2 carbons. This is going to be a CH2, and then this will be a CH3, and this will be a CH3. So propane means there's 3 carbons. 1 carbon, 2 carbons, 3 carbons. That's the condensed. Now the skeletal is going to be just like that. So this is a carbon. This is the chemical bond to the other carbon. And this is the chemical bond to the 3rd carbon. So in essence, this is going to be carbon 1, this is carbon 2, and this is carbon 3. That doesn't mean there's 3 carbons here. It's just indicating the 3rd carbon. Now, we typically leave the hydrogens off because hydrogen is ubiquitous in organic chemistry. And so a lot of times the hydrogens are left off. The next one is hexane. Now, that's going to be 6 carbons. So it's 1 carbon. That will be a CH3. This is going to be a CH2. This is going to be a CH2. This is going to be a CH2. So that's 1, 2, 3, 4, 5, and now 6. Now you don't have to draw it in this zigzag shape, but if you want to, that's fine. So that's 1 carbon, 2 carbons, 3 carbons, 4 carbons, 5 carbons, 6 carbons. That's the condensed. Now if we do the skeletal, it's going to be 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. All right. The next one is heptane. That's 7 carbons. So we're just going to add 1 more carbon to this. So that's H3C, CH2, 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 1, 2, 3, 4, 5, CH2, CH3, sorry, CH3. Remember, carbon has 4 bonds. So if this carbon is bonded to 3 hydrogens, there's 3, and then there'd be the 4th carbon. This carbon is bonded to 2 hydrogens, so it'd be a hydrogen here, hydrogen there, so it'd be 2 bonds, and then there's 3 and 4. Now the skeletal, that would be 2, 3, 4, 5, 6, now 7. So that's 1, 2, 3, 4, 5, 6, 7. Now the last one is cyclopentane. Let's hope if I could spell cycle. Pentane means 5. So that's going to be 1, 2, 3, 4, 5. And there's that. And then there'd be a hydrogen off here, hydrogen off here, hydrogen there, hydrogen there, hydrogen there, hydrogen there, hydrogen there, hydrogen there, and then a hydrogen down there. And how the skeletal, that would be something along that line, or you could draw it like a house. There you go. All right. So this nomenclature in drawing organic compounds is pretty important. As I mentioned, it can be up in excess of 10 million compounds formed from organic chemistry. You saw how long it took me to draw the condensed. A lot of times what you see is you see the skeletal, because the skeletal is a whole lot faster to draw, and it's easier to look at these structures than it is to look at all these hydrogens and all these bonds. And so a lot of times you'll see the skeletal structure. All right. Now the question asks, indicate whether each of the following pairs represents a structural isomer or whether it's the same molecule. Okay. To start out with, we're going to look at this group over here. What we have is we have one carbon bonded to 4 methyl groups. Here we have a carbon bonded to 2 methyl groups and an ethyl group. So to start this out, let's count the number of carbon atoms. So this is going to be 1 plus the 4 around it, which is C5. Count the hydrogens. 4 times 3 is going to be H12. Here we have a carbon bonded to 2 methyl groups and an ethyl group. So if we count the carbons, we have 1, 2, 3, 4, 5. So that's C5. Count the hydrogens, we have 3, 7, and 5 is going to be 12. So we have the exact same chemical formula, but they're just arranged ever so slightly. So their structure is different. So they are structural isomers, is what they're called. All right, we're back with another problem now. Once again, we want to determine whether these are structural isomers or if they're the exact same molecule. So what we have here now is we have 1, 2, 3, 4, 5, 6. We have C7. All right, we count the hydrogens. We have 3, that's 6. This would be 12. Add 4 more. That's going to be H16. Let's come over here now. And what we have is we have C, 1, 2, 3, 4, 5, 6, 7, C7. And if we count the hydrogens, we have 3, 3, 3, 3. That's going to be 12. We have 14, and now that becomes H16. Now, what we want to look at is these methyl groups, all right? So this, if we start counting the number of carbons, we have 1, 2, 3, 4, 5, all right? Here we have a methyl group coming off of carbon 2. We have a methyl group coming off of carbon 3. All right, so 2 and 3. Let's count this chain. 1, 2, 3, 4, 5. All right. Here we have a methyl group coming off of carbon 2. And here we have a methyl group coming off of carbon 4. So in this case, we had a carbon group coming off of methyls 2 and 3. Here we had them coming off carbons 2 and 4. Now, because those methyl groups come off of 2 different carbons, this is once again going to be referred to as a structural isomer. Okay. All right, we're back with another problem. Okay. Now, let's once again start counting up the carbons that we have. So once again, we want to determine whether these are structural isomers or if they're the exact same molecule. Here we have 1, 2, 3, 4, 5 carbons, so it becomes C5. We have 3, 5. 5 and 7 is going to be H12. Here we have once again C5, 1, 2, 3, 4, 5, C5. Count the number of hydrogens, 1, 2, 3, 4, so that'd be H12. All right. This is where it gets a little interesting with organic chemistry. All right. Let's see, we have these methyl groups, right? We have these methyl groups, right? There's got a methyl group right there. Let's see if these are on the exact same carbon. Now, if I count this as 1, 2, 3, 4, we know that it's going to be on carbon 3. If I count this as 1, 2, 3, 4, it looks like it's on carbon 2. What if I count backwards? There's no reason saying I have to go from this direction on. I could go backwards, right? Could have done that in either problem. Let's count this one. 1, 2, 3, 4. Now it's on carbon 3. If you take this molecule and you rotate it just like that, it becomes the exact same molecule. All right? There's no reason I have to count this direction one that way. I could count the other way. Notice that's on the exact same carbon. Carbon 3, carbon 3. Likewise, I could count this now as carbons 1, 2, 3, 4 of this chain. Here it appears on carbon 2. All right? So because it appears on the exact same carbon, this is going to be the same molecule. Now for this question, what it asks for is it asks for to draw the condensed structural formula as well as the skeletal formula for the following. So here we have 3-ethyl pentane. So pentane means we have 5 carbons, so I'm going to draw the 5 carbons out. 1, 2, 3, 4, 5. And off the third carbon, so this is 1, 2, 3, we're going to have an ethyl group. So that'd be a CH, 3, CH, oops, sorry, CH2, CH3. This becomes H3. This becomes H2. All right. This becomes an H. This is an H2. And this is an H3. Now these are all bonded together. All right. We bond. I just want to put the hydrogens in there. That's going to be the condensed. Better make my 2 a little bit better there. Now to do the skeletal, it's 2, 3, 4, 5. All right. Carbons 1, 2, 3, 4, 5. So this carbon refers to that carbon. This carbon is going to be that one. This carbon is this one. We happen to have an ethyl group. So now this carbon is right here. That carbon is right there. This carbon is right here. That carbon is going to be right there. All right. Now this one's a little more complicated. We happen to have 3-ethyl 2-methyl heptane. Heptane means we have 7 carbons. So we'll draw the 7 carbons out. There's 1. Let's start with CH3. We know that. This is going to be a CH. There's our second carbon. This is going to be a CH as well. This is then going to be a CH2. So this is carbons 1, 2, 3, 4, 5, 6, 7. All right, 7. Now off of carbons 3, so this is 1. Oops, sorry. This is carbon 1, 2, 3. Off carbon 3, we have an ethyl group. So I'm going to draw my ethyl group. That's going to be a CH2, CH3. All right. Now off carbon number 2, I happen to have a methyl group. So we could draw that going up this way. So it'd be a CH3. You could put it down there as well too, and that's perfectly fine. So this is going to be our methyl group. This is going to be our ethyl group. All right. Now how do we draw this in a condensed or in a skeletal form? Well, we have to do our 7 carbons. It's 2, 3, 4, 5, 6, 7. All right, so this carbon goes right here, this carbon right there. That's going to be a methyl group, so we draw that up. This carbon is going to be right here. This carbon is right there, so we have to draw now our ethyl group. So this carbon is right here. Make that the same length. And that carbon is going to be there, and everything else should be the same. All right? Back with another problem. So in this one, we have 4-ethyl 2,2-dimethyl octane. Once again, we're going to come up with the condensed and structural formulas for these. All right. So once again, we'll start with octane. Octane is going to be C8. So there's 1, 2, 3, 4, 5, 6, 7, 8. We can number these as 1, 2, 3, 4, 5, 6, 7, 8. All right. Coming off of carbon 4. We're going to have an ethyl group. So this is a CH2, CH3. Coming off the second carbon, we have a dimethyl, which means we're going to have 2 methyl groups. So that's CH3. Let me erase this. This is going to now be a CH3. All right, and then you just fill in the hydrogens. H3. There isn't going to be any hydrogens there. This is going to be an H2. That's an H. H2. H2. H2, H3. All right. Now to do the skeletal, I'm going to kind of erase this right here, and I'll write it right in this space right here. We'll use green. So we'll do C8. So there's 2, 3, 4, 5, 6, 7, 8. All right. So that carbon is right here. Second carbon is going to have 2 methyls. You can draw it that way if you want to represent the 2 methyls. Here's carbon 3, carbon 4 is going to be our ethyl group, which we've seen, and the remaining rest of the molecule remains the same. All right. 3-bromopropane. That's going to be, propane is 3 carbons. There's the 3 carbons. Off the third one, 1, 2, 3. We're going to have a bromine, so this becomes an H2. This is an H2, and that's an H3. Now, if you want to do the skeletal view of this, 2, 3, and coming off this one would be a bromine. And that's how you do nomenclature for alkanes. Remember, alkanes are going to be single bonded structures. All right. This next question asks nonane. Nonane has a density of 0.79 grams per milliliter, and it boils at 151 degrees Celsius. A. Draw the condensed structural formula and the skeletal formula for nonane. Nonane is going to have 9, so it's going to have 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's the 9 carbons. If you want to draw the skeletal, it's going to be 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. There's our 9 carbons. Is it going to be a solid, liquid, or gas at room temperature? Well, since it boils at 151 degrees Celsius, that means it's probably more likely going to be a liquid at room temperature. Is it soluble in water? No, this is going to be a very nonpolar molecule, so it will not be soluble in water. And will nonane float in water or sink in water? Well, its density is 0.79 grams per milliliter, which is less than the density of water, and the density of water is going to be 1 gram per milliliter. All right, in this problem, what it states is it says to draw the condensed structural formula for each of the following. Now, this is cis-1,2-difluoroethene. Now, this is a different ending than what we've seen before. The other ones we had ane. This is ene, which means it's a double bond. So all these are going to contain double bonds. All right, so for cis-1,2-difluoroethene, we have 2 carbons as such. All right, 1,2 means that there's going to be a fluoro on carbon 1 and a fluoro on carbon 2. But the cis tells us that it's going to be they're both going to be on the exact same side of the carbon bond. So there's going to be a fluoro here and a fluoro there. This would be a hydrogen. This would be a hydrogen as well there. Now what this means, the cis means that the fluorines are going to be either on the bottom, below the double bond, or they're both going to be on top of the double bond. If you have something that would be trans, for instance, in the next example, you'd have possibly one fluorine above the double bond, and you'd have another fluorine below the double bond. But since you have cis, that means that both are going to be on the exact same side of the double bond. All right. Now let's look at trans. All right. Let's look at trans. Okay. In this case, what we have is we have trans 2-pentene. All right. So let's just first draw the double bond. All right. So let's just first draw the double bond. And what this says is it says that the double bond is going to occur at the second carbon. So this has to be our second carbon. So there's going to be another carbon somewhere up in this area, okay? Now, because this is trans, now if we count 1, 2, 3, we're still missing 2 carbons because we have pentene, which means there has to be 5 carbons. And so we're missing 2 carbons, I apologize. We're missing 2 carbons. Where are those 2 carbons? Well, they're going to be bonded off of this carbon. But since this is trans, they're going to be below. All right. So these R groups for trans, all right. Trans means there's going to be one above and there's going to be one below. All right. So that's what it means to be trans. Okay. Now I'm going to erase this one so I have room for the octene. All right. So please give me a few moments while I erase. But just remember that cis means that the R groups, an R group is going to be anything other than hydrogen. It's going to be anything other than hydrogen, all right? And cis means they're going to be they're both going to be on the same side of the double bond. Trans means they're going to be on the opposite side of the double bond. So here we have octene, so we know we're going to have to deal with 8 carbons. But for right now, I'm just going to start with the double bond. Cis means they're going to be on the exact same side, all right? So they're going to be on the 4th carbon. So this is going to be carbon 3, carbon 2, and then carbon 1. So 1, 2, 3, 4. Double bond is going to occur on the 4th carbon. So 1, 2, 3, 4. 5. Now we're still missing 3 carbons. So it's going to be CH2, CH2, CH3. All right. I have a hydrogen here and a hydrogen here. Now since it's cis, these 2 R groups are going to remain on the same side of the double bond. Now they both could have been above the double bond as well too. I just wrote them below so I wouldn't run into what's going up on top. But the cis means that the R groups, so this is going to be an R group, this is going to be an R group, I wrote the prime as if they're different R groups, are going to be on the exact same side of the double bond. All right? Thus ends this chapter for Introduction to Organic Chemistry. If you have any questions pertaining to this stuff, please let me know. Have a good day.